All right, this lecture is going to be about a mathematical concept or a tool that we're going to use later in the week, and that is complex exponentials. So this is something that maybe some of you have seen before, but I'm guessing many have not. It's one basic math fact we want to use, and that is that if you have an exponential that has complex argument, so take for example e to the I theta, where I is the square root of -1, our complex number. It turns out that e to the I theta is equal to cosine of theta plus I times sine of theta. Okay, and this can be proved in the following way. If I consider the Taylor expansion of an exponential, so just to remind you, so if I have e to the x, and let's make x equal to I theta, the Taylor expansion is just 1 plus x, so 1 plus I theta, plus x squared over 2 factorial, so I theta squared over 2 factorial, plus x cubed over 3 factorial, and so on. So I can go on forever. All right, so that's the Taylor expansion. Now I can group these. There will be terms that will be real and terms that will be imaginary. So this is obviously real. This is imaginary. This is going to be real because I'm going to square the I and make it -1. That's imaginary. So let's group them. So if I take the real terms, I'll have 1 minus theta squared over 2 factorial. And it turns out that over here, there will be a term that goes like plus theta to the 4th over 4 factorial, and so forth. Okay, and now I can look at the imaginary part. So I'll have a plus I times, I'll have theta, and then I'll have minus theta cubed over 3 factorial, and it turns out I'll have plus theta to the 5th over 5 factorial. That's supposed to be a 5. Let's try that again. 5 factorial, and so forth and so on. Okay. Now, if I look at these two terms, it turns out that I know what they are. This is just the Taylor series for cosine of theta, and this is the Taylor series for sine of theta. Okay, so now we've verified that this expression up here is true. Okay. So you ask the question, who cares? All right. So let me give you two pieces of information. One that's a mathematical use of this idea, and then the second is why should we care about this in the context of this course? What does it have to do with simple harmonic motion? Okay, or oscillations. So first, let me just point out that using this idea, this complex exponential, I can represent any real number, any complex number, sorry, as a complex exponential times an amplitude. Okay, so if I take an imaginary number, so I'll write imaginary numbers with a twiddle over. So a twiddle will be some real part plus I times an imaginary part. Okay, so I can treat this kind of like a vector. So I can consider this to be in the x direction and this to be in the y direction. So I have a real axis and an imaginary axis. So I can draw that here. Okay, so here's my imaginary axis, here's my real axis, and the point A might lie right here. So here's A. Okay, and I can consider this like a vector, so consider it to be something with direction and magnitude. And so the direction is given by the angle it makes in this plane. Okay, and the magnitude is just the length of the vector, which will be the magnitude. Okay, and so I can write this as in component form, of course. So this, let me move this up a little bit. This will be the imaginary component, and this will be the real component. So what I have is that the magnitude of this number, okay, is going to be the square root of the real piece squared plus the imaginary piece squared. That's the length of the vector. And I know that the real part can be written as the length of the vector times cosine of phi, and the imaginary piece, I'll squeeze it in down here, can be written as the length of the vector sine phi. Okay? All right. So I'm representing this number in the complex plane. I can conversely write that um, down in the following way. So if I have the fact that this number can be written as a real plus a imaginary, that's the same as the magnitude times e to the I phi, where phi is that angle that I drew in the previous picture. Okay, and it turns out that you can find that angle just by taking the ratio of the real and imaginary piece and taking the arctangent. So the angle phi is defined as a tan, the arctangent of a imaginary over a real. And you can just read that off looking at that polar figure on the last page. Here, I'll go back so you can see it. Okay, so that angle phi can be determined by the magnitude of AI and AR. Okay. All right, so for any imaginary number, I can use this expression to write it in that way. Okay. All right. Okay, so that's one additional piece of mathematical definition that's useful for us. Now let's go on and ask the question, why do we care about this in the context of this course? Now, we've been talking about oscillatory behavior, and our oscillatory solution had been for the small angle simple pendulum for spring mass system. We had the following generic solution that solved our equation. Okay. Now it turns out that I can write this same expression down using the complex exponential. Okay, so it turns out, let's start with the following. If I have x, which is real, okay? So what I'm going to do is say, let's take the real part, which I'll denote as RE, of some complex number a twiddle times e to the I omega t. Okay? So if I now rewrite this using the two concepts from before, so I look up above now and I can write this complex number a using this expression. Okay, so I just replace it with a magnitude times e to the I phi. I can rewrite this as a magnitude, which of course is a real number, times e to the I omega t plus my phase factor. Okay? And if I now expand out my complex exponential here, I have the real part of a magnitude times cosine of omega t plus phi plus I sine of omega t plus phi. Okay, and of course that just gets me a twiddle magnitude. So this is just some real number times cosine omega t plus phi. Okay. All right, so this just shows that my oscillatory solution is equivalent to the real part of a complex exponential. Okay, now why is this useful? It turns out that it's much easier to solve these kind of linear differential equations using this guess that my solution looks like a complex exponential, knowing that when what I really mean is I take the real part of that, and what I get is this oscillatory solution here. Okay, so just to give you a flavor of this, how it can be useful, this concept in solving equations, let's go back to our simple harmonic motion equation, which is x double dot is minus k over m times x. Now if I make the guess that the solution x is the real part of, again, some complex number e to the I omega t. So what I'll do is I'll now use this guess in the equation on the left. But what I'll do is I'll leave the real, taking the real part to the end. So I'm just going to assume I'm going to replace x with a twiddle e to the I omega t, okay, and take derivatives. And then when I'm all done, I can solve for x and take the real part at the end. So if I look x dot, okay, what happens if x is just a twiddle e to the I omega t? Taking the time derivative just brings down a factor of I omega times a twiddle e to the I omega t. So this is the same as I omega times x. So what we see is with this assumption, time derivatives just become factors of I omega. So x double dot just becomes another factor of I omega times x, so it's minus omega squared x. Okay, and so this solves our original problem, assuming omega squared is k over m. Okay, all right, so it's not so profound here because we were able to find a solution for this equation without making a complicated guess, including this complex exponential business. Okay, but when we introduce more complicated systems of equations, or more complicated ODEs, this guess of complex exponential for the solution is very helpful. And let me preview. We'll talk about damped oscillators in class. So if I consider adding damping, so my previous equation just had a spring force, and that was it. There was no friction, nothing else opposing the spring force. But now let's consider some friction. And you can choose many different models for frictional forces. The one that we'll choose as a model is that the force due to friction will be proportional to the velocity. Now it turns out there's no friction force that's exactly like this. Okay, this will be a model force that approximates what it looks like, damping looks like in reality. So for example, this might approximate drag due to air. Okay, air drag as an object moves through the air. Okay, but if we just introduce this force, our equation becomes the following. So we have our equation of x double dot as before, minus k over m x, but now I have another force that goes like minus b, and since I've already divided through by mass, okay, I have to divide this by mass, and then I get an x dot. Okay, all right, and so this we have to solve this equation to see what the motion will look like when we add damping. Now we can guess physically what this is going to look like. It's going to oscillate possibly, okay, but it's going to damp. So you're going to see some decaying oscillation happening. And we could guess what a functional form would be for that. But it turns out that the complex exponential will solve this equation, and we can use that to kind of explore the solution now for this equation. All right, so if I go now and assume that x is real part of a twiddle e to the I omega t, and as before, I'm going to leave the real operation to the end. So I'm going to go in and pretend like x is just a twiddle e to the I omega t. Okay, and so I know when I take time derivatives, all I do is replace the time derivatives with factors of I omega. So this just becomes minus omega squared x. Okay, this becomes minus k over mx. There's no change there. But here I get a single time derivative. So this becomes minus I omega x b over m. Okay, and now I see that this guess of a complex exponential is a solution, okay, if the coefficients of all these x's, so I can cancel out all these x's, right? Okay, and it will be a solution if omega squared minus k over m and then minus I omega b over m is equal to 0. Okay, so this sets a condition on the frequency for this solution to be valid. Okay. All right, and so what I can do now is just, again, preview the solution. So what we're going to find when we solve that equation is that the frequency will be complex. You'll have a real piece of the frequency, and then you're going to have an imaginary piece of the frequency. Okay, so now if I go back to my ansatz, to my form of my solution, I have that x is equal to the real part of a twiddle e to the I omega t. Okay, and so let me take it one step further. Okay, as before, I can do real of a twiddle magnitude e to the I omega t plus some phase here. Okay. Now, if I plug in this solution for omega, so I know omega has a real part and an imaginary part, I can write this as real of a twiddle e to the I omega real t plus phase times, now I can break out the imaginary piece here, and so because there's an I times omega I, this just becomes minus omega imaginary times time. Okay, and this solution, the only complex thing is right here, so I take the real part of that. What I get is a magnitude cosine omega real time plus this phase factor times e to the I, sorry, not I, e to the negative omega I t. So what I get is what we might expect from our physical intuition, is that there's a damping here. So this is some exponential decay or damping of the motion due to the friction force. The force kind of saps energy out of the motion and it slowly rings down. So one solution that comes out of this process is you get a damped oscillator where the amplitude of the oscillation decays with time. So here's what this is going to be, a magnitude e to the minus I omega t. Is this omega, sorry. This is going to be a magnitude e to the minus omega I t. So this is the damping piece. We'll damp that oscillation. Okay, and I'll talk more about the physics of this in class, but what I wanted to get across to you here is this idea of using a complex exponential to represent an oscillatory solution, or as a guess for a system of for an ODE, and we'll use that again in class to consider damped oscillations.